Okay. Hello everyone, I'm Martini and I'll show you some of our investigations on fatigue strength of aluminum, silicon and magnesium alloys. I will skip on this since I think that we all know how standard additive manufacturing on metals works. I just want to focus on some of the pros and cons of this technique. Since it usually allows much easier customization of the components and it leaves way more room for structural optimization, and it also leads to the final component with way less processing steps. Unfortunately, it usually also brings some disadvantages like bad surface finish, suboptimal density, some tension or residual stresses, and also a little anisotropy. In order to reduce all these common defects, many post-treatment techniques can be applied, but you don't usually want to apply too many post-treatments since you might actually get too many processing steps to get to the final product, and then you would lose one of the main advantages of this technique. So we actually analyzed sandblasted specimens, since one of the problems of as-built additive manufactured specimens is that they usually don't have that grade of fatigue strength. And sandblasting is quite cheap, and it should be effective. Here are the machining specifications of our specimen. Specimens were vertically built with a little preheating on the bed. Specimen were then manually sandblasted with ceramic beads. The powder is the commercial powder by US, and as we can see, the composition is pretty standard. We actually carried out some preliminary analysis on the powder, and as we can see, the quality is very good since there is a very low intrinsic porosity with few porosities at a few micrometers level. And as we can see here, sandblasting already looks quite effective since the roughness gets a lot better, as we can see both on the top images and on the bottom images. On the right we have the sandblasted condition, on the left we have the as-produced condition. The surface looks a lot more uniform, and we also get some surface residual stresses that are positive for fatigue resistance, since we get from plus 70 megapascal to minus 100 megapascal on the surface. We carried out also a few preliminary static tests. There is nothing new here, since sandblasting doesn't really affect static properties, so the belt strength, ultimate strength, and Young modulus have standard values as compared when compared to as-built specimens. This is a little bit more interesting since this is the first result we were happy about, in the sense that our fatigue tests have a very small dispersion, while usually additive manufactured specimen might get to dispersive fatigue tests due to their porosities. All the tests were carried out in axial regime with a stress ratio of 0, and we can appreciate the low dispersion by looking at the dot line, which is the lower confidence limit calculated by using approach 1990, meaning that we consider 90% of the future population with a 90% confidence level. And this line is pretty close to the average line, so we were pretty happy about it. As comparison to some literature data, our specimen behave better, as we can see here, than as-built specimen, but of course worse than specimen that were post-treated with more expensive post-treatment like machining or ad hoc heat treatment. The performance were actually pretty comparable with aged specimen or preheated bad machined specimen, but when combining the preheating and the aging, specimen are actually performing a lot better. So let me skip on this we just see typical additive manufacturing microstructure. There's nothing new here. Melting pools on the in-plane images and typical half-moon melting pools on the z-axis in specimen, as I was told, are all manufactured along the z-axis. Here we can see one of the fracture specimen. It's pretty nice that we could clearly see on all the fracture specimen the three regions: crack nucleation, crack propagation, and overload. Then, since we wanted to go deeper into defect analysis, I put it out software within the National Instrument Lab environment to carry out automatic defect analysis of metallographic images. I will not dive deep into the details, but the software basically can process single or multiple metallographic images, and it leads to the most interesting defect features like defect area, defect orientation, maximum thread diameter, and defect position, and whatever you might think of. The software probably does it. This is what it looks like. So this is a stitch of 60 or 70, I think, metallographic images. So this image is pretty big. It's like 100 or 200 megapixels. This is a zoom in of the image, and I hope you see it. These are all the defects identified by the software, and every defect is evidenced in red. As you can see here from the Google image, you can get out like 1,000 or 1,200, I think, defects in just a few seconds. But since these data are like way too much, we decided to process data by applying a data binning technique, and we divided our cross-section domain into 12 radial bins, which basically are simply 12 concentric rings with the same thickness, right? And we just extracted a few features like defect area, radial defect distribution, and the maximum thread diameter. So this is the first finding, which we found really interesting in the sense that here we have the defect count per bin, which means that in each of these columns you can get how many defects there are in that specific ring. And here there is the cumulative, which is the same as not considering the ring, but considering a circular area. And as you can see here, there is a pretty clear linear trend and even a more clear quadratic trend here, which means that actually the defect distribution we could see here, which we consider a lot more defects in the outer region, is just due to a geometric effect. It has nothing to do with the manufacturing process, since it just respects the geometry that we are analyzing, since the area of a ring is linearly proportional to the radius, and the area of the circle is of course proportional to the radius to the square. So the areal density with respect to the radial position of the defects is simply uniform. Kind of the same we can see by looking at the average defect area per bin, in the sense that the average defect area doesn't vary at all along different radial positions. And this means again that the manufacturing process is giving us sort of a uniform distribution of porosity along the radial position. Now, this is also interesting since we also took into consideration the maximum thread diameter to check where the most critical defects were located. And in all the 4 samples we analyzed, the most critical defect, besides this sort of outlier, are in the outer region. Even though we actually are in the axial regime, this was also in good agreement with SEM analysis, which showed on every single fracture specimen that the crack was nucleating on the surface or on the subsurface. And we were really happy since we carried out this without having looked at the SEM, and when we saw that there was a really good agreement, we were pretty happy about it. So in conclusion, we just got pretty happy with our experiments, even though it's still a work in progress since we got a good agreement between defect analysis on metallographic images and SEM analysis. And we found out that it seems that there is a radial uniform distribution of the porosities, which is kind of strange since the current literature doesn't really talk about it, and it only focuses on the fact that additive manufactured specimens show a lot more defects on the outer region of the specimens. Thank you, everyone.
Thank you. So,